All right, let's talk about the unit circle and its relationship to trigonometric functions. So first off, what is a unit circle? A unit circle is simply any circle with a radius of 1, hence the name unit circle, the idea that it is 1 unit. So we can place a circle on our Cartesian planes. This is our x and y axis. And so we can see here, let's kind of zoom in on this unit circle here, that its radius is 1. R is equal to 1 here. And we can see that all the way around, no matter where we are, our radius is going to be equal to 1. Now, what we want to do is we want to be able to find the coordinates of points that are on this unit circle. So just understanding the fact that our radius is equal to 1, we can find certain points, like for example, this coordinate here would have to be 1, 0. This point up here would have to be 0, 1. And we should also be able to understand that this is negative 1, 0. Negative 1, 0, and this point down here would be 0, negative 1. That's not too bad, okay? However, what if I told you that we have an angle such like this, where this angle here were 30 degrees? Suppose this angle here were 30 degrees. Would I be able to find its x and y values? What is the ordered pair to represent that coordinate there? Understanding again that this radius is equal to 1. Well, the answer to being able to determine those points lies in our understanding of a special right triangle, or these special right triangles. If you think back to geometry, there was something called special right triangles. And the first example of one is something that uses the same angle that I just mentioned, a 30-degree angle here. Well, if this is a right triangle, meaning this is 90 degrees, and this angle here is 30, that means this angle up here must be 60 degrees. And it turns out that special right triangles have a special relationship, that the sides that are opposite these angles here have a pattern, or they follow a ratio. Suppose the side that is across from the 30-degree angle, so the side that is opposite of the 30-degree angle, let's just call this some unknown side. Let's say, for example, A. Well, the side then that is opposite of the 60-degree angle, it turns out that it's going to be whatever that A value was times root 3, or root 3A, okay? And the side that is opposite of the 90-degree angle, or our hypotenuse as it's also known as, is going to be twice the length as whatever A is. So what that means for us is that we can draw a special right triangle here on the unit circle. If this angle here is 30 degrees, what I can do is I can effectively drop a vertical from that point, and I'm able to then draw a special right triangle here, where if I drop the vertical, that means this angle is 90 degrees. This angle here, again, was given to us as 30 degrees. That means this angle here has to be 60. So let me just clear this out of the way. Well, if we know that is the case, then what do we know about our sides? Well, if we said that this side here is A, this side here is root 3A, and this side here is equal to 2A, remember that we are dealing with a unit circle, which means our radius is equal to 1. If that is the case, we can say that this side here, 2A, has to be equal to 1. Well, if our hypotenuse is 1, that means A is equal to 1/2. So let me replace that. This A then is equal to 1/2. And again, now if A is 1/2, we know that the side that is opposite of the 60-degree angle is root 3 times 1/2, or we can write this as root 3 over 2. Okay? And again, since our hypotenuse or our radius is equal to 1, we can say that this side is 1. So using what we know about a special right triangle, we can identify the side lengths of the triangle that we can draw here. Again, remembering that the side lengths ratio of a special right triangle would follow A root 3, or 2, and 2 as the last one. But if you look carefully at what we just did, notice that these side lengths actually correspond to the x and y values. That this side length here, this is also our x value. It's the horizontal distance up until this point. It's the horizontal distance up until this point. This is root 3 over 2. Let me clear this out of the way now that we know how we got that 1/2. And this value up here, this is our vertical distance, or our y value. This is our y value. So using special right triangles, we're able to find both the x and the y values for some angle that involves 30, 60, or 90. And if I wanted to, I could do this again for something like 60 degrees. Okay, so let me clear this out of the way, and then let's do now the angle for 60 degrees. So now that we've all done that, I'll just clear this out of the way. Let's start fresh. Let's try something for 60 degrees here. Well, if this is a 60-degree angle, just like I did before, I can drop my vertical down, make this a right angle. That means this angle here has to be 30. And again, knowing what we know, if our hypotenuse is going to be equal to 1, that means the side that is opposite of our 30-degree angle has to be 1/2. And the side that is opposite of my 60-degree angle is root 3 over 2, which again, this is my x value. So my x value is 1/2. And my y value, the vertical distance from the positive x-axis or x-axis, is just root 3 over 2. So using what we know about a unit circle, I could determine the x and y values for any angle that is a multiple of 30 or 60. And it turns out there's actually another special right triangle, and that's known as a 45-45-90. Let me just go ahead and do that here. Well, what about a 45-45-90 triangle? If it's a 45-45-90, that means it's an isosceles triangle. So if this side here that's opposite of that angle is A, that means this side that's opposite of this angle, since these angles are congruent, must also be equal to A. And the side that's opposite of our hypotenuse has to be equal to root 2A. So the ratio is A times root 2, whatever that side length or that leg is times root 2. Well, let's do this in the context of this unit circle here. So I'm going to clear this out again, out of the way. So if we have this angle here, where this is 45 degrees, again, I'm going to drop a vertical down. Let me switch color so we can clearly see our 45-45-90 triangle. If this angle is 45 degrees, that means this angle up here is 45. If we know that this is A root 2, and you know that A root 2 is equal to 1 because our radius is equal to 1, that means A is equal to 1 over root 2. And if we rationalize this, this would be root 2 over 2, which means then that our hypotenuse is equal to 1, and each of our legs is going to be equal to root 2 over 2. And again, we notice that those are both our x and our y values, so we can then determine that this coordinate here is root 2 over 2, root 2 over 2. So using what we know about our special right triangles, we can determine the x and y values, our coordinates, for any angle that is a multiple of 30, 60, or 90, as well as a 45-45-90. So let me just jump ahead now to us being able to fill in then our unit circle. So what have we just determined so far? That this angle here, which is 30 degrees, also known as pi over 6, this coordinate we just found was root 3 over 2, 1/2. This angle over here, I'm just going to kind of draw this going up this way. This angle up to this point, this is 45 degrees, or pi over 4. This we just determined had an x and y value of root 2 over 2, root 2 over 2. This coordinate up here, coming all the way up to 60 degrees, is going to be 1/2 root 3 over 2. We did that as well. And these angles here, since our radius is equal to 1, we already know that this is equal to 1, 0, and 0, 1. Now, what about if I wanted to keep going? And this, by the way, was up to pi over 2. And I'll just write the angles in radians from here on out. Well, what if I wanted to keep going? What if I wanted to find the angle here going all the way up to here? This is 2 pi over 3, or 120 degrees. What would be that coordinate? And so there's a couple things that we can leverage from our first quadrant understanding. First off, we can identify that this point here is simply going to be a reflection over the y-axis. So our y value remains exactly the same, but our x value is going to be simply the opposite. This is negative 1/2. So using that again, we can then say that this coordinate over here is a reflection of this coordinate in quadrant 1. So this is negative root 2 over 2, positive root 2 over 2, and you can just keep going with this. Negative root 3 over 2, positive 1/2, and this point down here would be negative 1, 0. And this is for the angles if I wanted to keep going, 3 pi over 4, and this would be 5 pi over 6, and now at this point I'd be up to pi. Now, are there any other patterns that we could leverage here? Well, one thing that I just want to literally highlight to you is the fact that look at our x values. Our x values all have denominators of 2, but you'll notice here that This is root 3 over 2, root 2 over 2. The square root of 1 is equivalent to 1. So this is also root 1 over 2. Root 0, or the square root of 0 over 2. And this point over here, actually, also, if I said the square root of 4, just to keep in the pattern, root 4, root 3, root 2, root 1, root 0, the square root of 4 over 2 is also just 1. So that also works as well. So there are a number of different patterns and things that you can use, but ultimately, take a moment, pause the video right now, try to fill out the rest of the unit circle for yourself. And once you've done that, you should see that you should get something that looks like this. Don't worry too much about any mention of the trig functions that you see here, but you can go ahead and just double check what you know about the unit circle and just make sure that you have these here. So hopefully that gives you a good understanding of how the unit circle works and how we can determine the x and y values for any angle from 0 to 2 pi. Now, going back to our lesson, now that we have a good understanding of the unit circle, the question that you might be asking then is, well, why do I need to know the unit circle? And the answer lies in our understanding of trigonometry. Trigonometry is effectively the study between relationships between angles and the sides of the triangles that those angles create. So, for example, if I took this triangle here, let me just kind of quickly draw this. If I had this triangle here, and suppose I were looking at this angle here, theta. Well, it turns out that all three of these sides have a certain relationship, or have a certain name. The side that is opposite of my angle here, the side that is opposite of my angle, I would call this directly my opposite side. The side that is directly next to my angle, but is not my hypotenuse, this is known as my adjacent side. And the side that is opposite of my right angle, or the longest side of the triangle, this is my hypotenuse. What the trig functions do is it evaluates the ratio of the sides from any given angle. So the first one that we should discuss is sine. The sine of an angle simply means to find the ratio between the opposite side compared to the hypotenuse. So the opposite compared to the hypotenuse. Cosine compares my adjacent side to my hypotenuse. And tangent compares my opposite side to my adjacent. And there's a number of different phrases that some people might learn just to help them remember this. The most popular being so, ka, toa. And if you're in my class, you've heard me say this before, but I actually never learned SOHCAHTOA until I took geometry. Prior to that, all I did was actually memorize the side relations. So I would often say, o, ah, oa, oa, oa. And you know what? It sounds ridiculous, but it helped me. There are also reciprocal trigonometric functions. So cosecant is the reciprocal of sine. So we would say hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. So these are the 6 trigonometric functions that we should be aware of. Again, what it does is it takes any angle and it compares the certain side lengths, whether it's the opposite compared to the hypotenuse, the opposite compared to the adjacent, and so on. But I haven't quite answered the question yet of how this relates to the unit circle. Well, it turns out we can take any angle at all, and let me actually make that a little bit smaller so this actually fits, and that works pretty well. We could take any angle and we can evaluate the trigonometric function of that angle. And what we can actually do is leverage what we know about our unit circle. Take, for example, the angle, if this angle theta were equal to 30 degrees. Well, we just established that this coordinate here, the x and y values of 30 degrees, or pi over 6, is root 3 over 2 and 1/2. And what we've already also done is we've said, okay, this adjacent side is also known as my x value. My opposite side is my y. And in a unit circle, my hypotenuse is always going to be my radius, which is equal to 1. Well, how does that help us here? If I were doing the sine of 30 degrees, and I know the sine of 30 degrees is my opposite compared to my hypotenuse. Well, I know that my opposite side is whatever my y value is going to be. My opposite side corresponds to whatever my y value is, and that's 1/2. Well, what is my hypotenuse? In understanding our unit circle, our hypotenuse, if we use 1/2, is always going to be equal to 1. So 1/2 divided by 1 is just 1/2. Which then we could take a step further and say, well, if we're really thinking about these angles in the context of the unit circle, my hypotenuse is always going to be equal to 1. And if that's the case, maybe I should highlight that instead of underlining. If that's the case, my sine of any angle is really always just going to be whatever my y value is. So we can think of sine being whatever your y value is. And on the same note, cosine would be whatever your x value is. And tangent, we could think of being y over x. And we could take that, extend that with our understanding of the reciprocal trig functions. This would be 1 over y for cosecant, 1 over x for our secant, and x over y for our cotangent. Okay? So if I wanted to do something like the sine of 45 degrees, what this then allows us to do, if we know our unit circle, is we don't have to sit there and draw a special right triangle every single time. We wouldn't have to sit here and do this, right? What we can say is, all right, we know that on our unit circle at 45 degrees, I'm just going to quickly draw this. At 45 degrees, my coordinates are root 2 over 2, root 2 over 2. Sine of 45 degrees is simply the y value at 45 degrees, which is just root 2 over 2. So knowing the unit circle is an incredibly powerful tool to allow us to evaluate trigonometric functions really efficiently. Okay, so these are the 6 trigonometric functions, and now we understand them in the context of the unit circle. So let's just do a little bit of practice with that. So what about an angle that goes beyond 2 pi over 3? Or it goes beyond pi over 2, I should say. So something like 2 pi over 3. So if I wanted to do 2 pi over 3 here, yes, I could drop a vertical and create a 30, 60, 90 triangle. If I wanted to, I could. That method is valid. However, if I know my unit circle, I know the coordinate at 2 pi over 3, the xy value, go ahead and check your unit circle if you need to, is negative 1/2 positive root 3 over 2. So that means that the sine of 2 pi over 3 is simply my y value here, because it corresponds to my opposite side, root 3 over 2. What about the cosine of 2 pi over 3? Well, that's going to correspond to my x value here, which is negative 1/2. So this is my y, this is my x, this is my quote-unquote opposite. And since my hypotenuse is just always 1, I don't really have to worry about my hypotenuse. Oops, and this is my adjacent. Tangent of 2 pi over 3, then, would just be my y over my x, root 3 over 2 divided by negative 1/2, which is just negative root 3. And really quickly, I can also do my reciprocal trig functions. Cosecant of 2 pi over 3, now that I know sine, I know it's the reciprocal of that, which is 2 root 3 over 3. Reciprocal, I should say, of sine. Secant of 2 pi over 3 is the reciprocal of cosine. And cotangent of 2 pi over 3 would then be the reciprocal of my tangent, which was here, negative 1 over root 3, or negative root 3 over 3 once we rationalize. So I don't have to sit there and draw special right triangles. I can quickly use my unit circle to efficiently evaluate these trig functions. Go ahead and pause the video right now and try to see if you can work through these next two on your own. Well, for this one here, pi over 2, hopefully we found that pi over 2 is up here, so this is 0, 1. My x is 0, my y is 1, and my hypotenuse, or my r value, is always 1. So sine of pi over 2 would just be my y, which is 1. Cosine of pi over 2 is just going to be 0 over 1, which is 0. Tangent of pi over 2 is y over x. So my y, 1 over 0, this is undefined. Cosecant of pi over 2 is the reciprocal of 1, which is just 1. Secant of pi over 2 is the reciprocal of 0 over 1, or 1 over 0, which is undefined. And the cotangent of pi over 2 would be 0, or the reciprocal of 1 over 0. Okay? And then what about for negative 3 pi over 4? Well, negative 3 pi over 4 would be this angle here. If we access our unit circle, we see that that's negative root 2 over 2, negative root 2 over 2. Then sine of negative 3 pi over 4, well, that is just going to be equal to our y value, negative root 2 over 2. I'm just going to say theta from here on out since I know what theta is. This is also negative root 2 over 2. Tangent of theta would be my y value over my x value, so that's just going to be positive 1. And then I can also do all of my reciprocal values as well. Also negative root 2. And cotangent of theta is going to be 1. Okay? So hopefully this helps understand not only the unit circle, but its relation and its helpfulness in us being able to evaluate trigonometric functions efficiently.